Thank you very much for the presentation. It's an honor to be here, also because it's my first time here in CIRM. So I want to deeply thank the organizers for giving me this very nice opportunity to talk today. So in this talk, I will disclose a very recent result containing a recent paper written jointly with David Krzyżyk from Prague. So in this very recent paper, we study the interplay between geometric deformation of bend and twisted tubes in the, for the nonlinear Dirichlet-P Laplacian, here defined as follows. In particular, we proved that if we consider bent and asymptotic straight tubes, the spectral threshold is pushed up, and so we get existence of discrete eigenvalues below the essential spectrum, while if we twist the tube, the spectrum is pushed down in the sense that we generate in the sense of RD-type inequalities. Actually, all these results we already know this result for the linear Laplacian, so it is P is equal to 2. So our motivation is not only into study the fact that these results also for nonlinear operators, but also to study the very natural generalization of nonlinear operator, that is the P Laplacian operator. So, well, considering bending tubes, the first result in this direction is contained in a paper by Exner and Seba in the two-dimensional case. In two-dimensional case. Then this result was generalized in the third-dimensional case by Goldstone and Jaffe with a very nice procedure, but not so. The mathematical approach was not so robust, and so 3 years later, Duclos and Exner improved the mathematical rigorous. Well, we have actually to wait some years to the generalization of arbitrary dimension by using the Frenet frame, and then the last contribution by using the adapter parallel frame is due to Krzyżyk and Serivadova, obtaining this result with the optimal regularities hypothesis. Well, roughly speaking, bending a tube means that the particle that is moving inside this waveguide gets trapped in this curved quantum waveguide. While if we consider a twisting tube, then this particle prevents for being trapped in it. And how can we see this property? By an RD-type inequality. Actually, as far as we know there is an RD-type inequality for the Laplacian, but only in the three-dimensional tubes. So actually our results are not only a generalization of this result for the P Laplacian, but also a generalization for the Laplacian, so with P equal to 2 for higher dimensional cases. And so I also wanted to report here this very nice lecture notes by David, from which I also take the nice picture that you will see in these slides. Okay, so of course we in the follows we take the natural generalization of the spectral threshold in green by using the Rayleigh characterization, and the person formula here in orange. And in what follows, we'll assume the approach by Das, Pinchover, and De Ver. And in particular, if we consider the nonlinear set of the P-Laplacian operator and a bounded domain, that we know that the infimum is achieved, so we have a first eigenfunction and a first eigenvalue. While if omega is unbounded, that is actually our case of tubes, the situation is not so easy. So in what follows, following the approach by David and Saradova, we consider a relatively parallel adapted frame, and so we define K as the curvature function of gamma, which is a C11 smooth unit speed curve, and we consider the following relatively parallel adaptive frame instead of the Frenet frame, because this type of frame requires less regularity with respect to the Frenet frame. And so, I mean, the usual way to dealing with quantum waveguides is to pass to curvilinear coordinates, and it is actually what we did. So after considering a family of rotation matrices, capital R, we introduce a mapping L, so that our tube can we consider as a modification of the straight tube, here omega 0, defined as R times omega, where omega, small omega, is the cross-section of our tube. And in what follows, we always consider that our tube does not overlap itself, and this assumption can be translated by the following condition in orange, where A can be considered as in some sense, the radius of our cross-section. And so, under this hypothesis, we'll have that L is a C01 diffeomorphism between omega 0 and omega kr, that is our tube. So, okay, sorry. So we have two possibilities that I will explain here. I mean, or if we consider capital L as a C01 diffeomorphism, and so omega 0 will be immersed manifold, or if we assume that L is injective, we can consider omega 0 as an embedding manifold. But by the way, in all these two possibilities, we can pass to the curvilinear coordinates. And so in what follows, we will use this definition of the spectral threshold, lambda 1, where Q of psi is defined as follows in orange. Okay, tubes. So in general, our tubes, I mean, we consider straight tubes when are equal to omega 0. So it is these images. And then if we consider k different than 0 and r prime is equal to 0, we are considering a non-trivially bent and untwisted tube like this one. While if we want to consider twisted in a non-trivial way, we actually have to consider a stronger assumption with respect to r prime different to 0, and it is this one in pink or magenta, and we will tell you why this assumption. And then we also consider as asymptotical straight tube, in the sense that is straight at infinity. Okay, well, this hypothesis is actually assumed. Why? In order to avoid that our tube is congruent to the straight tube. And since this is not very clear, I mean, at first sign, in dimension 3, this condition is equivalent to consider that theta prime is different from 0 and the cross-section is not circular, where theta is the angulus of this parametrization that holds, of course, in the third dimensional case. While if we consider higher dimensional, I mean, the situation is more complicated, so we have only a sufficient condition that it's actually this one, for example. Okay, so the first result is a result of stability of straight tubes, and it says that the spectral threshold of straight tubes coincide with the one in the cross section. Actually, this result was already proved by Brasco for general product spaces sets of this type, but I just want to spend some words also on it. So in particular, lambda 1 of omega, since small omega is bounded and connected, is positive and a simple eigenvalue of the Dirichlet-P Laplacian in our cross section. And so there will be also a unique positive minimizer phi 1, and we will choose it in follows normalized to 1 in LP norm. Okay, just a few words about the proof of this result. Why? Because even if this proof is, well known, here we can find a first difficulty when we dealing with nonlinear operators such as the P Laplacian. Indeed, if P is equal than 2, then here we have no exponent. But here for general P between 1 and infinity, we have this exponent here, so we have actually to use this kind of estimate in order to put this exponent inside the parentheses. And it is actually what we did in this other inequality, since the first one is quite simple to prove. And for the second one, we also have to define a sequence of function in W0, 1p, test the following behaviors, and we have to prove that this fraction goes to 0. Then, always considering straight tubes, we also prove that the stability of the P Laplacian with respect to more small perturbation, in a sense that W1 V of omega 0 is less than W1 of omega 0 when V is a non-positive and non-trivial C0 infinity function. And so just few words about the proof. So we actually have to prove that it is strictly negative, and so we have to split the proof into these two cases, and so things becomes more and more difficult. Okay, so just a few words about the behaviors of the shifted operator. So, we will prove that if we consider twisted tubes, then the shifted operator is subcritical in a sense that there exists an Hardy type inequality by following definition of Kazakh, Shrik, Lam, and Laptev. And while we actually have just proved that in a straight tube this is critical in the sense that such positive function does not exist. While for non-trivially bent tubes, our shifted operator is supercritical in the sense that we will show that this is negative, so it continues to be negative if we add, of course, a non-positive function. Okay, so what happens for asymptotically straight tubes? In this case, the essential spectral threshold is equal to the spectral threshold in the cross-section. So in particular, for straight tubes, it means that the essential spectral gap is equal to 0. Okay, so to prove this result, we have to split our proof into lemmas, because the lower bound actually holds for a more general hypothesis, so only for asymptotical and bent tubes, while for the upper bound holds for unbent, also untwisted tubes, asymptotically, of course. So for the lower bound, we have to define a special compact subset, capital K, defined as follows. And omega epsilon, in the case when omega is the ball of radius a, omega epsilon is the ball with radius a minus epsilon. And so after some calculation, we end up with this chain of inequality where this one tends to infinity by using the Faber-Cran inequality for the Dirichlet Laplacian, while this inequality tends to 1 because of this assumption, and so we can conclude. While for the upper bound, we have to consider any compact set, and so after some calculation, as you can see, it appears P over 2, so again, in this case, we always use the inequality that I showed you before, and so we have, you can see that these three terms, I mean, the first one tends to 0 according to this assumption, while the other one, this function, goes to 1. And so by using the definition, the definition, and epsilon sufficiently small, we get our conclusion. Okay, that's what happens for band tubes. Actually, for band tubes, we have this reduction of the spectral threshold in this sense only for circular cross-section, and this problem I will present in this afternoon for the open problem session, because actually this assumption is not needed for the Laplacian operator because it will follow by integration by part. But now we cannot use the integration by part, and so we have to be helped by symmetry in some sense. By the way, by this theorem, we get as a corollary the positivity of the essential spectral gap, in a sense that we get for a non-trivially bent and asymptotical straight tube with circular cross-section, we have this inequality here. Okay, and so why we have to consider omega circular? Because we really need these two inequalities, and that actually holds if omega is circular, and since in this case phi 1 is radially symmetric in balls and spherical sheets, that is the definition of circular domain. And why? Because this equality will help us in order to have this other inequality that is equivalent to this other two. So we have to consider circular cross-section or any type of domain that satisfying actually number 2 or number 1. Okay, just a few words about the proof. So we have to prove that Q1 here defined is negative. So we'll divide the proof into steps. For the first step, we take a regularization of phi 1 by the same sequence of function phi n. And also in this case, after dividing the proof into cases, we actually prove the asymptotic equality. While for the second step, we perturb psi n by psi n epsilon and prove the strictly inequality. How can we perturb this sequence? By, in this way, where phi is defined as follow, where it appears j a function of s and xi a function of t. That will be defined soon. But the very important thing is that psi and epsilon should be strictly greater than 0 if we are in the support of j. And this will be very important in the sequel. In fact, in what follows, we write Q1 of psi and epsilon as a function of epsilon. Then we use the Taylor expansion. And so from the first step, this term goes to 0, while in the other term is first and actually does not depend of n, also because of this assumption, and it is also negative. And so, we can choose n large to have the strict inequality. I'm sorry, I'm getting very fast, but trust me that we had a lot of calculus in this direction. Okay, what happens for non-trivially twisted tubes? We have a hard inequality. That means that there exists a positive continuous function rho such that this inequality holds. And this equality is equivalent to this other inequality by using the curvilinear coordinates. And so by using actually the approach of these two papers, we first have to define lambda 1n in omega 0 a L, which is defined in this way. And we first have to prove this following lemma, which states that the equivalence between the hypothesis, which leads to the assumption of untrivial twisted tube, and the positivity of this difference. And sorry, I don't have time to enter into details, but this lemma will be very important in order to state Hardy inequality. So as usual, we first state a local Hardy inequality in the sense that for non-negative and non-trivial function rho L, it is defined as in this way, where CL is this constant and it is positive by using the previous lemma. And so after having a local Hardy inequality, we get a global Hardy inequality by a very standard argument. So that's all, just a few words about future programs in this direction. So the first could be considering other type of boundary conditions, such as Neumann or Robin boundary condition, because also in the linear case, not really much is actually known. And another possibility is to adding a magnetic field to the P Laplacian. That's all, and thank you very much for your attention.